Welcome to my series, How to Algebra, where I teach you basic algebra topics. Today we are covering rational exponents. So hopefully you get something out of it, and subscribe, like, comment, let me know what you think, and I'll catch you in the next video. Hope you enjoy it. All right, so let's get right into rational exponents. First, we need to recall that if I want to take the square root of a number, we have to simplify it, breaking it down into its prime factors, 2, 3, 5, 7, and so forth. When you do that, we'll see that 48 in this example gets broken down as such. And if we want to simplify it, we're taught that we circle the pairs and that the pairs can be pulled out of the square root as a single number. So here we circle two pairs of 2. So each pair can come out as a single 2, making 4 root 3. All right, but yeah, we're taught that, but why? Like, why do we have to circle pairs? Why can I pull out a pair of 2s as a single 2? And what you're not being told is that when you take a square root, maybe you've been told this, I don't know, but typically you don't learn this until much later, is that it's implied that there's an invisible 2 that's attached to the radical, the square root essentially. Well, the number is called the index, otherwise known as the root. When you break down the radicand, the part inside of the square root, into its prime factors rather, the root tells you how many of the factors of like factors that you can group together and pull out as a single number. So in this case, since it's a square root, we would group together a pair, 2. If this was a cubed root, then you would group together 3 2s and you'd pull it out as a single 2. So that's essentially what's happening. And depending on what the root is, will depend on how many of the matching numbers you will group together, basically. So let's see an example. So for instance, if I have the 6th root of 64, this is what I want. I want to simplify the 6th root of 64. So I need to break down 64 into 2 and 32, 2 and 16, 2 and 8, 2 and 4, and then 2 and 2. So essentially, this is going to be 6 2s. Because it's a 6th root, I want to group together 6, and I can pull that out of the radical as a single 2. So what this is saying is the 6th root of 64 is going to be just 2. If we get to something a little bit more complex, here we have the cube root of 48, x cubed, y squared. So 48 breaks down to 2, 24, 2 and 12, 2 and 6, 2 and 3. Because it's a cubed root, I can group together 3 2s, and this will come out as a single 2, and then left behind 2 times 3, which is 6. We have x cubed, so right, x cubed is really x times x times x. So I can pull out these 3 x's as a single x. And then y squared, it's only 2 y's, so they stay behind. Let's see another example. The cubed root of 27, c to the 9th, y to the 15th power. Okay, so breaking down the number, we're going to get 3 and 9, and 9 is 3 and 3. So again, group of 3, because it's a cubed root, I can pull out a single 3. All right, c to the 9th. Now, I mean, I guess I could write out 9c's, but if you think about it for a moment, if you divide 9 by 3, you're going to get 3. So that means we'd be able to pull out 3 c's essentially. So that would be c cubed. Right. So I guess maybe I'll demonstrate it one time. So if we were to write out 9 c's, here's a pair, or I guess a group of 3. Here's a group of 3, and here's a group of 3. So I can pull out each one as a single c, and c times c times c is just c cubed. That's why it's c to the third power. Same goes for y. There are 5 groups of 3 inside of 15. So I can pull out 5 single y's. So this would be 3c cubed y to the 5th power. We say all that just to say that when it comes to rational exponents, right, the thing that we're covering today, any root can be represented as a rational exponent, meaning an exponent that's a fraction, right? Because that's what a ratio is, right? A fraction. So a rational exponent is basically an exponent that's a fraction. That's what a rational exponent is, right? That's what a ratio is, a fraction. So a rational exponent. So here we have the a, or the nth root of a, meaning n could be any number, and we can represent this root as a rational exponent, meaning a, base a, to 1 over n. 1 over n would be the power. So if you think about the way a plant or tree works, or looks rather, the roots grow underground, right? So that's the way that I was taught to remember it, is that roots grow underground. So when you want to convert a root with a radical into a rational exponent, the root, the number that is the index basically, that's going to be the denominator in the rational exponent. It's the bottom number, right? Because roots grow underground. So that's a good, I guess, device to remember how it works. And the power is always on top. So if you look at the root, you'd say, well, where is the 1? Well, the 1, it's implied that it's on the variable, right? When we say x, we don't say x to the first power. It's implied that it's to the first power. So the power that is on the variable, that is going to go in the numerator of the rational exponent. And the root will go in the denominator of the rational exponent, again, because roots grow underground. With that being said, let's continue with the examples. So here we have the cube root of a over b squared. Now, it can't be simplified anymore, but it can be rationalized because we don't like any radicals in the denominator of a fraction. So if we rewrite this as a to the 1/3 power, right? Because again, right, 1 is the power, 3 is the root, so it goes underground, as we mentioned. The denominator will be b to the 2/3 power. Okay, so we don't want radicals in the denominator of a fraction. We know that. Since we can represent any radical as an exponent, we don't want any rational exponents in the denominator of a fraction. So the trick is going to be, we're going to multiply this thing by 1, right? Because you can multiply anything by 1 and not change the value. So let's recall, if I had this type of problem, to rationalize the denominator, we're taught that, okay, if we multiply it by root 2 over 2, root 2 times root 2 are going to multiply and the square root's going to go away. So 2 is going to be left in the denominator, and root 2 is going to be left in the numerator, or be in the numerator. So this same kind of idea, I have to multiply b to the 2/3 power by something. And the question is what? So if you think back to the exponent properties, when you multiply common bases, you add the exponents. So the exponents, in this case, 2/3, I need to add something to it to make 1. That's the trick. So it's going to be 1/3, right? Because 2/3 plus 1/3 is 1. And that's what we want, because then that'll get rid of the radical in the denominator. So what I'm going to multiply the top by is the same thing, right? Because anything over itself is 1. So this is just a clever one, so to speak. So the denominator is going to be just b, essentially b to the first power, but it's implied that there's a 1, so I don't need to write the 1. And in the numerator, a to the 1/3, b to the 1/3. And that's it. I mean, could you combine these to make ab to the 1/3? Sure, but but that's, I guess, subjective of what's simple. To me, this is simple. So this is as simple as it gets. All right. Cube root of 54, x to the 4th over 2y. So we can simplify this. 54 over 2 is going to be 27. So the cubed root, 27, x to the 4th over y. All right, 27 can be broken down into, well, we did this already once. 3 times 3 times 3. It's cubed root, so I can pull out a group of 3 as a single 3. This is going to be 3, and then x to the 4th power. So it's 4 x's, so I can pull out a group of 3, and there'll be 1 x left over. So I can pull out an x, and left behind is going to be the cubed root of x over y. Okay, so we're almost done. We have to rationalize the denominator, meaning I don't want any radicals in the denominator. So this will be x to the 1/3 over y to the 1/3. And I'm going to multiply this by y to the 2/3. Again, you multiply common bases, you add the exponent. So 2/3 is what we need, top and bottom. So this is going to be x to the 1/3, y to the 2/3 over y. So I guess final answer would be 3x, x to the 1/3, y to the 2/3 over y. We'll do one more example. 5 over 20, or the 4th root of 5x over 20y squared. So simplifying, we get 5 goes into 5 once, 5 goes into 20 4 times. All right, this is going to be x to the 1/4 power. I'm going ahead and write it as a rational exponent because I know we need to anyway. So the more you do these, the faster you'll get. The denominator will be 4y squared, all to the 1/4 power. So a couple thoughts. Couple ways of doing this. What would be the most efficient? So if we multiplied the denominator by 4y squared 3/4, we could do this, but I feel like there's a better way. So I think would you agree that 4 is really 2 squared? And since it's 2 squared times y squared, then the square can actually, in a sense, be pulled out of the parentheses. And this would just be 2y squared to the 1/4 power. When we have a exponent raised to an exponent, we can multiply. So really the exponent in the bottom is going to be 2 over 4, which is 1/2, essentially 1/2. So 2y to the 1/2 power. That's what's going to be here. So 2y to the 1/2. It's a little bit better, right? Like the number's a little bit more cleaner, I guess. But there was nothing wrong with doing it the way we were going to do it originally. So I'm going to multiply by 2y to the 1/2, top and bottom. So our final answer is going to be x to the 1/4, 2y to the 1/2 over 2y. That one's fun. Okay, let's look at, all right, so simplifying, I guess, rational exponents. 25 to the 1/2, that's just the square root of 25. So square root of 25 we know to be 5. 64, we already worked that one out as well. We know that, well, 64 is equal to 2 times 2, 6 times, right? And since it's a cubed root, right, because it's a 1/3 power, we want to group them in groups of 3. So a single 2 and a single 2. So ultimately, it's going to be 2 times 2, which is 4. That's good. Rewriting the rational exponent. So again, roots grow underground, so this would be 12 to the 1/3 power. That one's easy. Here, this is going to be 10 to the 1/3 power, raised to the 7th power, which means we multiply the exponents. So this is going to be 10 to the 7/3. So do we want to go through all of these? Sure, why not? So 49, right? Square root of 49, 7. All right, 125. Cubed root of 125, right? 125 to the 1/3 power. If we break this down, this is going to be 5, 25, and then 25 is 5 and 5. Again, a group of 3. We can pull out a single 5. All right, so a quick important note is that even roots cannot have a negative inside of the radicand, under the radical, basically. Odd number roots, however, can. So with that being said, if I want to take the square root of negative 81, it's not possible, right? It's a complex number. It's going to be a complex number. So we know that this would be 9i, right? Because the negative would come out of the square root as I, and the square root of 81 is just 9. So this is definitely a complex number. However, when we have odd number root, you can have a negative inside of the radical, it turns out. So here, negative 32. If we break down negative 32, this would be negative 2 and 16. 16 is going to be negative 2, negative 8. Negative 8 is going to be, right, because negative 2 times negative 8 is positive 16. So then negative 8 is going to be negative 2, 4. And this is going to be negative 2 and negative 2. So negative 32 is actually negative 2 times negative 2, 5 times. And if you multiply these out, because it's an odd number, the product will be negative, right? Like your end result will be negative. If it was an even number, then it would not be negative. So take that for what it's worth. Ultimately, odd number root, you can have a negative inside of the radical. That's what we're learning here. So fifth root, right? So I want to group together 5. It just so happens conveniently there's 5. So here, the fifth root of negative 32 would be negative 2. It's kind of interesting if you think about it. All right, moving right along. How many more of these do we want to do until we get the point across? Let's see. So 25 to the negative 3/2 power. So we don't like negatives in the exponents. So we know that this is going to force the 25 to go into the denominator. And it's going to make the exponent positive. All right, so what this is saying is that if I rewrite this, this is going to be square root of 1 cubed. I guess one thing I didn't mention earlier, it's worth mentioning now, is that when you have a power inside of the radical, you could actually pull the power out. That's one of the properties that's really nice about doing this, or I guess knowing it is nice. So if you have a power that is on the part inside of the square root, you can pull the power out. So that's why here the square root of 1 is 1. 1 cubed would be 1. So in this case, it's actually to our advantage here. And then particularly on this next part, so you're going to take the square root of 25, because that's the root, and we're going to cube it. So we're going to see that we're going to get 1 over, square root of 25 is 5, and 5 cubed is 125. So that is the answer here. Okay. 7 3/4 times, or raised to the negative 4 power. So when we can multiply the exponents, and this is going to cancel, making 7 to the negative 3, which is going to force the 7 into the denominator, and it's going to be, well, technically, it's going to be like that. Then ultimately, it's going to be 1 cubed. Right? Yeah, I can cube the top and then cube the bottom. So however you want to look at it. 7 times 7 is 21. No, 7 times 3 is 21. 7 times 7 is 49. 49 times 7 fifth is going to be, what's that, 63, 12, 28. So 343, is that correct? Yep. So 1 over 343. Okay. I think we'll move on to the last two and then call it a day. Try to keep this kind of short. Solving for x. So we can use what we learned, the properties and the rationalizing of exponents to solve algebraic expressions, solving for x basically. So if I want to multiply common bases, so here we have the common bases are 3. We add the exponents. So 3, 2x plus 5, right? Because 2x plus 5 is in fact 2x plus 5. There's nothing we can do. And then 3 to the 22nd power over 3 to the x. So it's always top minus bottom when the bases match. How in this case, it's the bases are 3. So it's going to be top minus bottom. So 22 minus x. It's always top minus bottom. There are other ways of doing it. This is the method I like. So now that the bases match, right, everything's matching, we can set the exponents equal to each other. And this is just your basic one variable problem, right? So I'm going to add x to both sides. 3x plus 5 equals 22. I'm subtracting 5 from both sides. 3x is equal to 17. Last step, we see that x is equal to 17 thirds. Okay, the last example I want to look at. Here we have an exponent raised to an exponent. So we're going to multiply. This is going to be w. And then the 4s are going to cancel, right? Because that's essentially over 1. So top times top, bottom times bottom. I have something in the top that's also in the bottom, so you can cancel it out. So this is going to be w to the x power, which is equal to multiply common bases. So we're adding the exponents. 5x plus 6. Again, the bases match, so we can equate the exponents to one another. And this is already looking nice. So this is going to be minus x, minus x, minus 6, minus 6. So we have negative 6 is equal to 4x. And then divide both sides by 4. X is equal to negative 3 over 2. Oops, can't see it. X is equal to negative 3 over 2. All right, well, I hope that this was easy to follow. If you haven't already, subscribe, like, comment, let me know what you think. Go ahead and call me out for my mistakes. That's one of the things about making these on the fly is that, mistakes happen. And hopefully you learned something. I'll catch you in the next video.